This is the introduction lecture for the digital electronics and integrated circuit course. And in this lecture, we will go over some introductory concepts. And the very first thing is that we'll go through brief history. I'm not going to spend a lot of time on it. We'll go over it very quickly. And if you need more in-depth knowledge, you can obviously always go to the book and read more about the history. But the important thing is that we have to understand that the purpose of integrated circuits is that we can have many transistors in one chip. That's the purpose. Why do we have integrated circuits? Because of this capability to pack many transistors. And obviously, many transistors means functions, performance. We can do and execute algorithms, etc. The the branch of engineering that deals with packing many transistors is referred to as very large integrated scale, very large scale integration, which is abbreviated as VLSI, which is really the engineering techniques and technology that is that focuses on integrating as many transistors as we can on a single chip. So very large scale integration is the branch of engineering that deals with that. And we have a course that follows after this DIC course that is the LSI design. Now, obviously, there are two methodology or two technologies that deal with packing transistors. One is the BJT technology, which is an old one, and the other one, a new one, is the complementary metal oxide semiconductor, abbreviated as CMOS. But CMOS won this competition because it is faster, cheaper, lower in power, and scales better with technology. Okay. So will address in the beginning of the course the BJT transistors and how you can build simple gates with them, and then we'll do that for one chapter, and then move on and focus the rest of the class on CMOS because it's the newer and the vast majority of integrated circuits are built using CMOS. Okay. Now, the other thing here we're going to look at is that history. Kind of interesting to see where we were and where we are now. And remember, this is almost like 10 years old image of a die. The point here is really making transistor smaller, and more of these transistors. So we are miniaturizing these transistors, and we are packing more of them on a single chip. Notice that this is the initial technology, and this is where we are right now. Huge, huge improvement on the transistor capability, on the capability of packing transistors on a single chip. Okay, to read about those, and obviously I'm not here, it's not history class, so read just for your own benefit, and see how this technology progressed in the last century and early in this millennium. Now, you see that this annual revenue growth in semiconductor industry obviously is growing faster and faster, driven by the miniaturization. Obviously, miniaturization has helped packing more transistors with hardware, and we should not also diminish the role of software in the compilers and in the application programs. So the hardware and software both are have excelled tremendously to give this incredible revolution of electronic industry that we are witnessing. Okay, so now you can see here is the annual sales. This is numbers in US dollars, and these are the years. You can see that this growth is exponential. This is an exponential growth and obviously sometimes it goes up and down with some kind of local dipping here, but overall it's exponential growth. So you can expect this to continue for the foreseeable time, that the electronic systems will have more and more in terms of US dollars in the sales. Now, of course, we have gone a long way from the first point contact transistors to where we are right now. In 1974, John Bardeen and Walter Brattain at Bell Labs, they have uh, started this single step in this revolution, and obviously everybody came in and added um, one step in this evolution, and then we have reached this incredible capability of integrating transistors in a single chip. Again, some historical perspective here. Okay, as we said, we have two competing technologies. We have BJT and we have CMOS. Okay, so somebody who says, okay, so what's the difference? Well, major difference with BGT, they are driven by current, and basically the collector current is magnifies the base current. This is when we are in the active region, and so it's a current-driven transistor. It typically has been very difficult to make it smaller and integrate it in large integration circuits, and that's why sort of this is the old technology, and then people moved to CMOS technology, and this is where voltages apply to kind of turn on and off a gate, and that was very well suited for low power circuits. So we were able to create circuits with lower power. More importantly, that the CMOS circuits were easier to scale down compared with the BJTs. So because of power, because of scalability issues, easier to scale, CMOS has been the dominant technology in implementing integrated circuits. BJT is sort of the old type of transistors, and that's why we cover them in this class, but kind of passingly. Okay, again, these are kind of from the past here. You can see how an SRAM and a microprocessor, the organization, the technology, these are the kind of stuff in the 70s and the 80s, some kind of historical perspective. Moore's law, Gordon Moore predicted that in every 1.5 years, every 18 months, we will double the transistor counts. So for instance, if I am in 2000, let's say 20, January 2020, my technology allows me to pack 1 billion transistor in an IC. Then by June, by June 2021, I should be able to pack 2 billion transistors in an IC. Why? Because every 1.5 years, number of transistors packed, manufactured in an integrated circuit doubles. Of course, you can take this further and say, okay, well, by January, okay, let's see, by January 2020, let's see, 21, and then 23, I can pack up to 4 billion transistors in an IC. Again, why? Because every 1.5 years, I can double the number of transistors. That's why you can see this exponential growth here. Somebody who says this is linear, I say no. Pay attention here to the y-axis. it is logarithmic, scaled logarithmically. So that's why this line is linear. Okay, so all right. If these are the number of transistors that are in packed in a core, this data is old, but you can see that this is again linear because the y-axis is logarithmic, and you can see this exponential growth in number of transistors that can be packed in a CPU versus the time. Okay. Now, the other thing is that one of the things that help us to or enable this to integrate more and more transistors, that the ability to shrink feature size, meaning the size of a transistor is shrinking 30% every 2 to 3 years. So if we have the transistor feature size 1 micro, after 2 to 3 years, we can shrink it up to 2.7 micro, etc., etc. So that ability to shrink the transistor has had help to pack more and more transistors in our devices. And again, it's almost like decaying exponentially. Okay. All right. So these are some of the feature size from the past and from the present, and you can see from the 70s, 90s, and then in the millennium here, the feature size, we can say it's the size of the transistor roughly, but throughout the course we will explain more what we mean by feature size. It's actually the channel length, but let's just take it right now without any details, and then we'll talk about it later on. You can see that when the feature size was a quarter a micron and more, we refer to these devices as long channel. And when the feature size less than quarter a micron, we call those short channel. And this is really will enables us to understand some of the rules and some of the laws and formula. They will differ from between long channel and short channel. Observe right now that we should be around 5 nanometer, but I should say that the growth or the decay here in the feature size has faced some technological issues that's kind of slowed it down a bit. Okay. This is now plotting the clock frequency, the speed of devices, and versus time. It's almost like, again, exponential, but you can see in latest years, kind of this thing leveled off because it's very hard to keep cranking up the clock because of jitter issues and skew, etc. So it becomes very hard to deal with, and that has had kind of made it making the clock faster a bit difficult. Now, our main material in creating semiconductor devices is the silicon, and the silicon, because silicon has this interesting feature. It is from group 4 in the periodical table, and this is the silicon crystal, where it kind of bond with its neighbors, and under this condition, the silicon does not conduct any electricity, and it doesn't have any current. But when I have the dopant, when I have um, I add to a dopant either from, oops, this is flipping faster than I expect. So this is so from I add a dopant from group 5. Well, I'm gonna stop this for a second. Okay, so let's see. Okay, so if I add a dopant from a group 5, right, which is in this case right here, right, um, which is in this case right here, from group 5, or I add a dopant from group 3, sorry, this is group 5, and this is from group 3. So this dopant material, uh, Okay, so we add a dopant material to the silicon from group 5, we end up with an N-type material, and basically this is because we have excess electrons. And if we add dopant from, so notice this excess electrons taken from this material of group 5, and if we add dopant from group 3, we'll have an electron taken away from the silicon atom. So this silicon atom here is referred to as a hole, okay, versus here the silicon atom we have an excess electron. So this create here a p-type material. And so basically in an n-type material we have excess electrons, and in p-type material we have excess holes, which is the absence of electrons. Now abutting or kind of if we add the p-type material and abut it with an n-type material, we create the diode as you have taken in electronics 1, and that is one of the basic circuits that is used in electronic circuits, the diode. And also we can use the p-type and n-type material to create a transistor of the type of CMOS, where I have a kind of a source and a drain separated by a gate, which is this one here. So this is the source, this is the drain, this is the gate here, and here I have a polysilicon material and isolated from the body by an SiO2 silicon dioxide material. We'll study this more, but here is the message here. Using an N material and P material, I was able to create a device. Okay, all right. So now the purpose of the transistors, basically in all of them, whether it's CMOS or BJT, they go into these on and off states, which enables me to conduct or to uh, not conduct. So that's really the on and off case of a simple switch, and that maps directly to Boolean algebra, where I have ones and zeros. That's why we like these transistors. They have this two states of on and off, which maps to 0 and 1 in Boolean algebra, and that's why they are used to build electronic circuits and computers. Okay. So this is one example here of a simple circuit that we will use and study it extensively throughout this course, which is the CMOS inverter, which consists of a PMOS, a transistor, and an NMOS transistor. And we'll study what is an NMOS and PMOS transistor. But this is just a general sketch here for you to understand that this is the basic inverter gate that we will kind of study it in this course. So this is the circuit schematic, and this is the logic symbol, and basically this is the truth table. Obviously, whenever the input is 0, the output is 1 because it is inverter, and when the input is 1, the output is 0. Okay, so again, introductory material. We're not diving into many of the details just yet, and we'll go through the details throughout the course. So this concludes our introductory material, which I want you to the takeaways is that the Moore's law, where we pack or we double number of transistors every 1.5 years, that every generation of transistors we shrink the size of the transistors, the feature size, about 30% every 2 to 3 years, and that had led to exponential growth in number of transistors packed in a IC. Clock frequency increases exponentially, although they are leveling off nowadays, and the sales are going through exponential growth as well. We have our basic material is the silicon. When we add to it an and a dopant from group 5, we end up with an n-type material. From group 3, we end up with a p-type material, and n-type conducts electricity and p-type conducts electricity, but the pure silicon does not. That's why we call it semiconductor. We looked finally at the circuit of the inverter, where we have a PMOS and an NMOS device, and we will study this later on, but just to show you that the schematic of the circuit and the logic symbol and the truth table of this inverter, which will be used later on. Thank you very much, and we'll see you in other lectures.